Hello, my name is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar, What's New in SigmaXL version 9. This is part 3 of 3, Control Charts for Autocorrelated Data. The webinar will be approximately 45 minutes long. We'll have 15-minute question and answer. For the questions, if you could please type them in. You can type them in during the webinar, but I won't get to them until the end. And then I'll read the questions out and respond. The webinar is being recorded, and in a couple of weeks it'll be available for viewing. And we post a notice on Twitter and Facebook and LinkedIn that it's available, as well email. And the workbook and the data sets, the workbook comes with version 9 under the help. So any example that I will demonstrate today is also in the workbook, so you can go through at your own pace if you want to replicate any of the exercises or the examples. As well, the data sets are available. This PowerPoint presentation is also available for download. So with that, we'll look at our agenda. So there's going to be a little bit of overlap with part 2, not too much, but just a little bit of overlap on the time series forecasting. And then the focus of the session is on control charts for autocorrelated data. So I'll kind of review the subject of autocorrelation, introduction to the problem of autocorrelation for control charts, introduction to autocorrelation. The example that we looked at in part 2, chemical process concentration, we'll revisit and create a control chart on the residuals. We'll reintroduce simple exponential smoothing. We'll look at the airline passenger data that we looked at in part 2, but this is a modified version of the airline passenger data where I've deliberately injected an assignable cause at data point 50 and a shift in the process at data point 100. So makes it a little bit interesting to see how the method works if we can pick up on those injected signals. We'll briefly review the error trend and seasonal exponential smoothing models and the autoregressive integrated moving average ARIMA models. We did look at ARIMA with predictors. The focus will be, of course, on using that tool for control charts. First, to use the predictors to distinguish between, is the assignable cause an outlier or is it a shift in the process? And then we'll look at a third example, electricity demand with temperature and workday predictors. And then we'll do Q&A. So with that, we'll start into the presentation. So statistical process control for autocorrelated processes typically use the exponentially weighted moving average one step ahead forecast model. The idea, the time series model forecasts the motion in the mean, and an individual's control chart is plotted of the residuals to detect assignable causes. If you have autocorrelation and you just run a regular individual's control chart, that will produce limits that are either too narrow, resulting in excessive false alarms, or limits that are too wide, resulting in misses. But if there's seasonality, negative autocorrelation in the data, it's not so simple, and the user needs an advanced level of knowledge in forecasting methods to pick the correct model. So whether to use exponential smoothing or ARIMA is one thing, and we discussed this in part 2 and said either or, depending on the data, you can look at the forecast errors as well. You can take averages, but on the control charts, the issue is that if you have a seasonal model, which one do you pick? And that's where the automated process comes in and selects the best model. You can specify a model, but we make it really easy for you by going through and picking the best model with the lowest AICC criteria. So we'll review simple exponential smoothing, exponentially weighted moving average. and then look at recent developments in time series forecasting that use automatic model selection to accurately pick the time series model that produces a minimum forecast error. An accurate forecast for your time series means that the residuals will most often have the right properties to correctly apply a control chart, thus leading to an improved control chart with reduced false alarms and misses. This is a recap of the new menu in SigmaXL version 9 under time series forecasting. We have the run chart, autocorrelation plots, cross-correlation plots, seasonal trend decomposition plots, spectral density plot, exponential smoothing forecast, exponential smoothing control chart, and this is what we'll be focused on today. ARIMA forecast, ARIMA control chart. We will also be using the ARIMA control chart and utilities. So to recap, autocorrelation, just as correlation measures the extent of a linear relationship between two variables, autocorrelation measures the linear relationship between lag values of data. A plot of the data versus the same data at lag k will show a positive or negative trend. If the slope is positive, the autocorrelation is positive. If there is a negative slope, the autocorrelation is negative. And this is the autocorrelation function formula. We're not going to be looking at formulas, but just to mention them. And for more information, you can always refer to the SigmaXL workbook. So in this example, this is the chemical process concentration data. You can manually copy and paste, or you can to create lags, or you can use the lag utility. But basically, you can see that the data has been shifted down one. And then we do scatter plots, and we look at the relationships, the data against itself lagged 1, 2, 3. We also show the correlation coefficients. So any correlation coefficient that is significant will be greater than approximately 2 over the square root of n. And that significant autocorrelation will result in detrimental performance on a Shewhart control chart. We also have the Legendre box test, and that's useful from an overall autocorrelation test and is very sensitive to tell you if there's any autocorrelation in the data. The ACF plot, each vertical bar corresponds to a correlation coefficient, and these first bars are above the significance line. So you can see, in this case, for the chemical concentration data, we have significant autocorrelation. This is a run chart of the chemical process concentration data. And what I've done to illustrate is I have an individual's control chart. So this is just a regular Shewhart chart on the chemical process concentration data. Because it has this wandering mean with autocorrelation, we have 17 out of control data points. Okay, well, that's a problem if you have something like this going on, because that's a lot of alarms going off and there's no actual assignable cause tied to these alarms. Some guidelines from Bill Woodall and Fred Fulton. If possible, one should first attempt to remove the source of autocorrelation. So that's something to keep in mind. If you can remove it, then of course it's better to remove the autocorrelation and just use a regular control chart. Secondly, if it's possible to use a feedback control scheme to reduce the variability about a specified target value as a way of dealing with this autocorrelation, that's also recommended before you implement SPC for autocorrelated data. However, there are many situations where the wandering mean is an inherent part of the process, and what you want to do is you want to use SPC to detect assignable causes, but you have this problem that native or inherent to the data is autocorrelation, and that will generate false alarms. So that's what we want to address using time series forecasting. So we start with a simple single exponential smoothing model, also known as the exponentially weighted moving average, or EWMA. And this is the formula. The forecasts are calculated using weighted averages, where the weights decrease exponentially as observations come from further in the past, with the smallest weights associated with the oldest observations. Okay, so basically as the data gets older, the weight gets less. So we then use that to make a prediction. And you can vary alpha. If alpha is 0.8, then you have a very rapid drop off in the weight. And if alpha is 0.2, then you have a very slow decay. So the older data has more influence. And the question is, what value do we use? Well, in a regular control chart situation, you would typically use 0.1 to 0.2. However, for this situation, we want to use Solver or the software to solve for the alpha value. So this is the formula, a simplified or a summarized version of the forecast formula for exponential smoothing. Alpha is used in time series forecasting. In a control chart application, lambda is more typically used. They're both the same formulas, they just use different nomenclature. So we're making a prediction, and we have the predicted value is lambda times the current value plus 1 minus lambda times the current EWMA value, or forecast value. Then in a regular control chart, EWMA control chart, you're not so much interested in autocorrelation, you're just interested in rapid detection of small changes. But that's different from what we're doing here. So it's the same tool, but a different application. And what we do is we solve for the lambda or the alpha by minimizing the sum of squares errors, the residual error, forecast error, one step ahead forecast error. And that gives us the optimal value, parameter value to use. And then that's what we go ahead and we plot the residuals on a control chart. So what we want, our residuals should be normal, independent, and identically distributed. If this is achieved, then we have the assumptions necessary for a Shewhart control chart. Okay, so that's really what we're going after. Recall from part 2, we have our exponential smoothing forecast dialog, and we can do automatic model selection or specify the model. In this case, the model is error is additive, trend is none. That's an EWMA. And then this creates an exponential smooth forecast. The red line is the one step ahead forecast. These are the prediction intervals and the prediction value for the 24 periods. Now in control charts, this part, the forecasting part, is really not important. What we're interested in is the actual one step ahead within, and then we control chart the residuals, the difference between the observed and the predicted. One thing we do want to do is compare the before, the raw data, ACF, to the after. And in this particular case, the model has done a good job of removing the autocorrelation. So the ACF plot on the residuals, it looks very good. And that would indicate that this is we can go ahead and control chart the residuals. Also, you'd want to look at the things like the normal probability plot, which is roughly normal, and histogram. And so we go ahead and we create a control chart. So now I'm going to switch over now, because now we're ready to create our first exponential smoothing control chart. So we'll come over here to the chemical process concentration data and time series forecasting, exponential smoothing control chart, control chart. So the dialog is very similar to the dialog for the forecast. We'll specify concentration. I'm going to turn off the ACF, PACF plots because we've already seen how the model works with that. And I'll turn off the display residual plots. So that's optional. If you hadn't run the forecast, then you'd want to turn these on. We're not using Box-Cox transformation here. This is something that, again, if you have an increase in variance over time, you'd want to use a box-Cox transformation. We don't have any seasonality in this data. It's non-seasonal data. So under model options, we can specify a model, or we can do automatic. We'll just go ahead and do automatic. So no change there. And we click OK. And this gives us our first control chart. Now, before we had 17 out of control data points. Now we have 2 out of control data points. So this is a Shewhart individuals chart on the residuals of the EWMA model. This chart uses the one step ahead prediction as the center line, and you can see now the control limits move with the predicted value. So it's essentially, it's the same chart as this, but this chart allows you to see the actual data. This chart is better. The individuals chart on the residuals is better for taking action on assignable causes. And this chart is better to just actually see what's going on in the process. So they kind of complement each other. Now, let me just to recap, if I do a regular control chart, so I'm just going to go in and I'm going to do an individuals chart on concentration. So it's just a regular Shewhart individuals control chart. And as you can see, you got lots of signals, 17 out of control data points, and it would be worse if we turned on test for special causes. Okay, so that's the reason we want to use, we have autocorrelation, so we want to use, in this particular case, the simple exponential smoothing model worked well. Although, just want to point something out, when I went automatic, rather than using additive errors, it chose multiplicative errors. I can scroll down here, and we saw this in part 2 as well, that the model, based on minimizing the AICC, chose simple exponential smoothing with multiplicative errors. So it's not exactly your normal EWMA. But that's the whole idea, is that the software is helping you to automatically pick the best model. A couple of things I'd like to point out in terms of control chart features. We have under SigmaXL chart tools, we can enable scrolling. So let's say, for example, I'd like to zoom in, and what I'll do is I'll start at 40, and then I'll make the window width of 30. What that allows me to do is that allows me to have a closer look at the signals of interest. And you can also scroll. You can scroll back through your data with whatever window width you selected. Okay. Another thing, let me just restore that. And the other thing we have that's a nice feature is the ability to add data. So if I come back here, and let's say I have a new data point, 198, and I'm going to say 19, and then I go to my control chart, and I click add data to this control chart, so it updated with the new data point. So it's important to note, I'll go back to the slides on this. When we do this, the model is not being re-estimated. It's simply adding the data to an existing control chart, and it's updating the residual value and plotting that on the control chart. So as you can see here, we have an out-of-control data point. And this is important for real-time or phase 2 application of the control chart. And that's where you would want to investigate assignable causes and then take corrective action or process adjustment applied. Okay, so that's the individual's control chart. Okay, so next we're going to go to example 2, which is the airline passenger data. And we saw that in part 2. We won't recap everything that we did in part 2 with the forecasting part, but what I've done is, first of all, I'm taking the logarithm of the monthly airline passenger data because there was some increase in seasonal variance over time, so we wanted the logarithm to get rid of that. In part 2, we used the Box-Cox transformation. So in this data, I have the data is modified with a negative outlier at 50. So at 50, this point here is actually an outlier, but it's really hard to see when you look at the raw data. Then also at 100, we added a shift. These are a small outlier and a small shift. So it's modified airline passenger data. If, however, you plot a control chart on this data, it's meaningless. It's really can't use it for SBC purposes because all of these are out of control signals, which is what you would expect. It's trending up, you have seasonality, lots of autocorrelation. All right, so that's, again, we saw the ACF plot. You have the scallop due to the seasonality, and you have a long-term trend with very strong and positive autocorrelation. We're going to use the error trend seasonal model to expand on simple exponential smoothing to accommodate trend and seasonal components as well as additive or multiplicative errors. The simple exponential smoothing model is the error model. Error trend is also known as Holt's linear or double exponential smoothing. And then there's error trend seasonal, which is a Holt Winters, also known as triple exponential smoothing. So again, we discussed this in part 2, so we won't spend much time on it, but just as a reminder, we're going to use this and apply it for control chart purposes. So to recap, this is the general dialog allowing you to specify as additive or multiplicative, trend, either none, additive, additive damped, seasonal, none, additive, or multiplicative. Those are your model options, and we're going to use the automatic model selection. So it'll go through all the combinations and pick the best model. So if we run the forecast with automatic model selection, this is what we get. We get an additive trend, additive seasonal, additive errors, Holt Winters model. Follows the data quite nicely. You can see this point here. This is actually the assignable cause that was added to the data or injected into the data. And now let's see, it's not really that obvious though, and that's the thing, we want to use the control chart to try to detect that. The model itself does a good job of removing the autocorrelation. You can see this is the raw data and this is the residuals. And now we're ready to go ahead and run the control chart on this data. So this is my monthly airline passenger data, and I will run SigmaXL, time series forecasting, exponential smoothing control chart, and we'll select lawn of airline passengers. We're going to come back. ARIMA will be used with predictors to look at the outlier versus shift problem. So that's coming in a little bit. Right now, we just want to do a control chart on the lawn of airline passengers. We're going to use automatic model selection. And the seasonal frequency for this airline passenger we know is 12. It's monthly data. Okay, so with that, I'm going to run this. And this is our individual's control chart. And recall that I added an out of control point at 50. It picked it up. It actually picks up a signal at 50 and 51 because the model is kind of thrown off. And there's that shift at 100. So you can see the control chart did a very good job in picking up those signals. Versus if you just were to run a regular control chart, let's do that, just a regular control chart on the lot of airline passengers. And as you can see, you've got all these out of control signals. So effectively, it's an unusable chart. Whereas this chart tells you very nicely where you have your assignable causes. So it did a really good job of detecting those signals that were present in the data. And then, of course, more importantly, going forward, that you would detect assignable causes, changes in the process, and then take corrective action. But this just illustrates how it works and how well it works. So this is the dealing with seasonality using exponential smoothing. We can also look at ARIMA, autoregressive integrated moving average models, which are complementary to the exponential smooth, and they use an autoregressive component and a moving average component. And we build a model on using order lowercase p, integrated differencing component lowercase d, and a moving average component lowercase q. And then for a seasonal component, we have uppercase p, uppercase d, and uppercase q. And these are model orders that are used in ARIMA. We touched on that in part 2, and now we're going to use it for control chart purposes. So in the dialog, you can specify the order. So this would be an example of a 011011, which actually works very well for the airline passenger data. And we will actually use the automatic model selection. If you run the forecast, again, this is something we did in part 2, so I won't repeat it. But if you run the forecast, you basically get a very nice prediction. It follows the data well, and it's an ARIMA 011011 model. Now, what we want to do is we want to use this. Oh, and as you can see, the before versus after, autocorrelation on the raw data versus autocorrelation on the residuals. The model has effectively removed the autocorrelation as well. We see the same on the partial autocorrelation. So now let's go ahead and do the control chart on this data, or sorry, the ARIMA. It's actually not going to be really much different, but it's just showing that you have some options. So ARIMA control chart, and then again, lot of airline passengers. Model options will be automatic, seasonal frequency of 12, and I'll go ahead and run that. And you can see here, it's very similar to what we had with the exponential smoothing model. A little bit different, but effectively it does the same job of detecting those assignable causes at 50 and 100. One difference to note is that there are no plot points on the first 13 data points because the model does differencing. So a seasonal difference of 12 takes out 12 data points. And then we did a non-seasonal difference of 1. So that's a total of 13 observations that are not shown on the control chart. Basically, you don't have residuals for those first 13 data points. Okay, so that's a slight disadvantage of the ARIMA, but the ARIMA may be preferred, depending on your data, maybe a preferred alternative. If you have negative autocorrelation, often the ARIMA does better than exponential smoothing, for example. However, if you have predictors, then that's where you need to use ARIMA. So let me go back to the slides. And here ARIMA with predictors. ARIMA model supports continuous or categorical predictors, similar to multiple regression. If you're doing a forecast, you must apply additional predictor values. However, we're not interested so much in forecasting as we are in producing a control chart, and that's basically a one-step ahead forecast. So it's a different application. We're using the model and we're control charting the residuals, looking for those assignable causes. Again, you have to be careful with your predictors. You don't want predictors that are strongly correlated. So the first example with ARIMA with predictors, what we're going to do is I created 4 columns. These are dummy code, and basically the first column is at the 50, that's a 1, and all the other values are 0. A shift of 50, what I've done is the previous values are all 0, and then the following values are all 1. And then at 100, we have this 1, dummy code 1, at 100, and then the shift is all the values subsequent are 1. So it's just simply dummy coded predictors, exogenous variables that we can use to distinguish between whether the assignable cause is an outlier or a shift. That's really what we're doing here. So there's a little bit of manual setup to do this. So go back to the worksheet. If I go back to sheet 1, we already have this set up. So what I would do here, I'm not going to create a control chart, but I'm just going to do forecasting. So time series forecasting, ARIMA forecast, forecast with predictors, and again, lawn of airline passengers. And what I'll do is I'll take these 4 and I'll put those in as continuous predictors. And we'll just go ahead, put in the seasonal frequency of 12, because again, it's monthly data. And we'll run that. So we're doing ARIMA with predictors, and these are dummy coded variables. And now the primary interest is what's significant and what is not. So you see the outlier at 50 is significant. The shift at 50 is not significant. The outlier at 100 is not significant, but the shift at 100 is significant. So it's a little trick you can use to take advantage of the ARIMA with predictors, and as a way to distinguish if you have some assignable causes and you're trying to determine whether they are due to a shift or due to an outlier. Okay, so that's one application of ARIMA with predictors. And we'll move on now to doing control chart with predictors. And for this example, we're going to do daily electricity demand with temperature and workday predictors. This is the data we looked at in part 2, is the daily electricity demand in Victoria, Australia for the year 2014. Remember, summer, winter is flipped. So this is actual summer weather, high demand, and this is also December. So this is also interesting because what we're looking at is demand. In the wintertime, you have increased electricity demand because of heating, and in the summertime, you have increased electricity in demand because of cooling. And if you plot this on a regular control chart, you get lots of out of control signals, again, because of the autocorrelation in the data. And this is the ACF plot from the prediction, ARIMA with predictors, so lots of autocorrelation, and you can see that 7-day cycle. You can also run a spectral density to confirm the frequency. The seasonal frequency is 7. This is what you would expect from daily data that follows a weekly cycle. So there's a Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday effect. Previously, with the airline passenger data, we were looking at a monthly effect. This is the daily. You can also do seasonal trend decomposition plots. We're not going to do that, but this just breaks out the trend, the seasonality, and you can, this is a seasonal component, the 7-day seasonal component, this is the trend. and the remainder. So the three of these add up to give you the original data points. So it's an additive decomposition model. Again, we're not focused on that today. We're focused on the control chart. But this is just to remind you of the data that was used. And also, this is the demand versus the temperature. So summertime, wintertime in Australia, summertime. And if you look at the relationship, you can see a quadratic relationship between temperature and demand. And there's also a slight effect on whether it's a workday or a holiday. And so a box plot is used to compare the demand for a holiday versus a workday. You can see that on a workday, there is greater electricity demand, and that also is expected. So the thing is, you know that workday matters. You know that there's a day-to-day seasonal effect, day of the week seasonal effect, and there's also this relationship between temperature and demand. And you want to put it all together and build a predictive model. And we did that in part 2. So you have demand, you have temperature squared, you have workday as a categorical variable, and a 7-day seasonal frequency. And this results in a very nice predictive model that allows you to then predict out. In this case, we showed a 2-week forecast for electricity demand. The focus now is not on forecasting, but on the application of control charts. This confirms that the model, it's not a perfect model. There is still some remaining autocorrelation. So possibly the model can be improved, but it's not a bad model, and it can still be used for forecasting purposes and for control chart purposes. So now we'll switch over and we'll go back daily electricity demand data. And we're going to create a control chart. So a ARIMA control chart with predictors. And I will do demand as the Y, put my date as my optional time axis label. Temperature and temperature squared will be my continuous predictor. And then I have workday as a categorical predictor. I have a seasonal frequency, so I'm changing that to daily. So seasonal frequency of 7. I don't need the ACF plots. I don't need the residual plots. We've already done that when we did the forecast model. We don't need Box-Cox transformation, and we're not doing any withhold on this data. We're just building the model with all the data that we have, the 1 year's worth of data. And we're going to control chart the residuals. This takes a little bit of time because it's a fairly complicated model. So it just takes about a minute or so to go through. And keep in mind, it's also doing the automatic model selection. So it's considering various orders of autoregressive, differencing, non-seasonal differencing, seasonal differencing, ARIMA, non-seasonal, and ARIMA seasonal. So it's working its way through using a stepwise routine to come up with a model. And there we have, so if we scroll down, there's our model with our temperature squared, and workday. We already saw that in our presentation in part 2. But what's important here is now the control chart shows just a few assignable causes. So we had some unexpected high demand early in the year, in January, and we had some unexpected low demand in December. So that's what makes this particularly useful, is that it separates out the signal from the noise. And so these would be the things that you would want to try to understand why we had these signals, why the model, the data was significantly different from what the model predicted. That's basic, that's your control chart on your residuals. And if I were to do just a regular control chart on demand, so just a regular individuals chart, So as you can see here, we have many more signals. So yes, you have the ones that we see from our ARIMA prediction model, but in addition, you have signal, 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 signal. So there's lots of false alarms. And again, as was the case with the airline passenger data, regular shoe-heart control chart on that data is not really very useful. But by building a control chart that not only takes into account the autocorrelation, but the effect of temperature, temperature squared, and workday, you have a very nice, powerful predictive model and a very useful control chart to help you to, in this case, because you're trying to predict demand, to help you to have a better understanding of anomalies between the actual demand and the predicted demand. So that concludes my presentation, introducing you to control charts for autocorrelated data. But I just want to also mention that due to time limitation, I did not show things like multiple frequency. That's another capability within the SigmaXL version 9, is that if you have data with multiple frequency, so for example, there might be a monthly component, a weekly component, a daily component, we can use decomposition to address that and also create a control chart of the residuals for that type of data. Let me just mention something that's not really part of the formal presentation, but just to make you aware, we added a couple of features in version 9.01, something called convert to discrete. So this is kind of a different topic altogether. I'll just open up the customer data, but it's on the topic of what's new in version 9. It just has nothing to do with forecasting. So let me just get the customer data. So a couple of utilities that are nice to know about that are in 9.01. We have what's called convert to discrete. So let's say you have continuous data and you want to convert it to discrete so that you can use continuous data as categorical. So let's say overall satisfaction. So what that does is that uses the quartiles, because I specified 4, and it converts this continuous data to discrete data. Then this can then be used as an X, a category X, for graphical analysis. So obviously, continuous is good for scatter plots and regression, but there may be some cases where you want to actually take your continuous and convert it to discrete. So that's a new feature in 9.01. And then another thing we added in 9.01 is under graphical tools called a multiple X box plot. And with a multiple X box plot, I'm going to do overall satisfaction, and I can pick these. Again, these have to be category variables. So I'll pick customer type, I'll pick size of customer, major complaint, product type, and I'll run this. And what it will do is it will create, it takes a little bit of time to crank through, it's about a minute, but what it will do is it will create a box plot, a row of box plots for comparison purposes. So just thought I'd mention that. And there we go. So here's our customer type, size of customer, and major complaint, and product type. So it's just another called a multiple X box plot, allowing you to quickly compare your discrete X factors across. This was something that previously we had multiple box plots, but they were nested categories. This way, if you want to view your box plots with multiple X's, you can do that. So I just thought I would mention that. Okay, we're going to call it a wrap. Thanks, James, for your note, from James from Denmark. And I appreciate everybody's participation. So thank you all very much, and have a great holiday as well. Thank you. We'll do some new webinars in the new year.